Good morning. Good morning. Isn't it nice to be back in school? Well, thank you all for coming. I'm Kevin Jaffe. I'm a faculty member in the department, and I currently serve as the department chairman. And I am now the 8th department chairman, and I have the honor of being chair for this momentous event. So thank you all again for coming. We're all here, as you know, to celebrate the 50th anniversary of the department. I'm sure most of you know the story of the founding of the department in one form or another, and it's documented on posters around the building over there in Sitterson, and I encourage you to go back and refresh your memory about all of the details. But what I would like to reflect on a little bit this morning is really the bold vision that was computer science in the mid-1960s, that, you know, 50 years ago this building wasn't here. Sitterson wasn't there, Brooks wasn't, well, Fred was here, the building. The Brooks building wasn't there. And there was this tiny, tiny little building that sadly is gone, West House, just down the road, that started off computer science. And so it started with one man being chief cook and bottle washer for the entire program, teaching all the courses, juggling 2 jobs, trying to hire faculty, trying to get the students, has evolved into a massive enterprise that spans 2 buildings. And during the course of preparing for the 50th, I've had the sheer privilege and delight to travel around the country and meet with alums. And the thing that strikes me about it is that the one common thread throughout the 50 years has been the excitement about computing. I mean, Fred created this department, he found some faculty, and some students showed up. And why did they show up? Because they thought this computing thing was pretty cool and exciting, and they had this love of discovery, love of knowledge, and they wanted to learn. And that happened through the 70s and the 80s and the 90s. And so although what computer science is today is fantastically more sophisticated than computer science 50 years ago, the thread that I think transcends all of these 50 years has been the excitement that you have all had for technology, for computing, and for learning. So we have a great technical program that's going to have talks from alums, all of you, about your experiences, your results, your thoughts. And what I encourage everyone to do is, everyone from an older generation befriend somebody from a younger generation, and each of you discover what was really cool and exciting about computing when you were here. I've always found that the older alums find the new work that's going on fantastically exciting, and in fact that the new alums find the old work fantastically exciting. It's like, really? You did that? So, you know, whether it was getting excited about seeing a single scan line appear on a raster display, or taking a bicycle helmet and kind of strapping on a little display and then trying to put it in front of your eyes and focus on it, or trying to schedule every resource in an OS so that you could drive a DSP so that sound would come out of a computer. Who thought of that? So it's always been exciting. It's always been exciting, and it's always been great. And you made it great. So this is really a celebration of the department, but the department is you. It's all of us. So it's really a celebration of you folks and everything that you've done. So today we have a series of talks spread out in the lower lobby of the Sitterson building and the Brooks building, and we'll have a series of keynotes back here. So the initial keynote obviously is now, and then we'll have a keynote after lunch with Ramesh Raskar, an afternoon keynote from Ivan Sutherland, another keynote at dinner tonight from Mike Ryder, and then my colleague Henry Fuchs will conclude the program on Sunday morning with his keynote. So you should have a map of all the locations in the program along with the schedule. And I think if you're like me, you read this, it sounds very, very exciting. This has been an absolutely Herculean effort to pull off, because it's not just this event, it's the fantastic amount of prep that came up to this event. Most of the staff is out doing many things behind the scenes, so we won't try and thank them now. We'll thank them more formally at the banquet tonight. But as you're walking around the building, you see folks with the name tags and it says staff on it. Say thank you to them. And they would love to meet you and also hear about what computer science was, what staff did when you were a student here. This notion that somebody typed your dissertation for you, you know? That actually makes them very nervous. So back in the lobby, there's an information sheet that you can pick up that has all sorts of helpful tips if you're concerned about being off the grid for today. There's Wi-Fi access provided by the university. The details are here. If you have any special needs, have a little medical issue, first aid, lost and found. I left my jacket at the reception last night. That's over at the front desk as well. So that's a handy little cheat sheet. So without further ado, I'd like to open the technical program, and to do so, I'd like to introduce my colleague, Dr. Henry Fuchs.
Thank you, Kevin. I also want to welcome you here. It's so wonderful to see those of you for so many generations. But I'm not going to take up more of your time. I got my slot to talk to you about old times tomorrow. I get to introduce Marc Levoy, who many of you know. But since some of you don't, let me say just like 2 or 3 minutes about him. When he came here in 1984, he was already quite accomplished. He had finished a master's degree in 1978 in Cornell University, and his master's thesis, for those of you that wonder, does a master's thesis worthwhile? His master's thesis on an animation system using computer graphics system was adopted by Hanna-Barbera. He went to work for them. They used it in production till 1996, something like that. I mean, imagine this, from 78 to like 1996, an amazing achievement. And he was working there till like 83. Then he came here for a PhD. He did phenomenal work on volume rendering and medical applications. After that, he went to this little place called Stanford University, where he was for many years. Those of you in graphics know that there was just a series of results that are milestones in computational photography, in light field rendering, in applications from the largest things to things microscopes. He was also active in all kinds of things in Google that you may not know about, and I'm not sure how much I could allow you to tell, but he'll maybe talk about some of it. Suffice it to say, he is now full-time, and I think has been for a while, at Google, and he is professor emeritus at Stanford University, still has students there, bicycles one day a week to Stanford, and 4 days a week bicycles to Google X. Without further ado, Professor Marc Levoy.
Thank you, Henry. All right, so it's really wonderful to be back here, just to smell the spring leaves. It's dry in California, in case you hadn't heard. All right, so what I'm going to talk about today is mobile first. So in the OKRs of all Silicon Valley companies, meaning the objectives and key results, they always talk about mobile first. And it's become an important sort of key post or signpost for the whole valley. And I'd like to go into that in a little bit and talk about what are the challenges of mobile first and what it might mean for the future of computer science, both research and teaching. But before I begin, I don't want to spend much time reminiscing, but I at least want to share with you my strongest memory from grad school when I was here. So as Henry said, my dissertation was on volume rendering. And so here's a hand-drawn illustration from my dissertation where we're tracing an array down through a voxel grid, and the voxels are density functions that might have come, for example, from computed tomography slices. And I would resample the voxels and then composite in order to produce this three-dimensional rendering. So I was coding it up. I had no idea what the images would look like, but I felt like I was getting really close. So what I did was I decided to pull an all-nighter. And so the computer graphics lab was at that time in Phillips Hall. And so I spent the whole night there alone. And at 4 in the morning, I thought I got the program running, and I hit carriage return, and I got a $sign back, which meant probably just like crashed immediately. And I'm sitting there trying to imagine what happened. And I happened to glance over at the frame buffer display, And staring at me from the frame buffer display was this image. So, remember, it's 4 in the morning, and I'm alone. Sometimes you think your soul is on display. Well, and what I thought of actually at that point was a quote from Richard Hamming's You and Your Research. And I know it's gender politically incorrect, but this is what he said, and that's what I felt at the moment. So, all right. So what does mobile first mean? What's that? Oh, I'm sorry. I'm sorry. Let me try that again. There you go. All right, I'll read it. The emotion at the point of technical breakthrough is better than wine, women, and song put together. I told you it was politically incorrect, but there it is. Richard Hamming. All right. So what does mobile first mean? So first of all, it means that it is happening because smartphones are outselling other forms of personal computing. And this gap here, the smartphones are the blue area here, and desktops and laptops are the green area at the bottom. And so I'll show a number of these sort of info porn slides. And as a result of that, the companies that work in this space are saying, first of all websites should be mobile friendly, and so that's an announcement that Google made recently, and that's being called Mobilegeddon. So you should be able to book a table, or book a flight, or transfer money from one bank account to another from your mobile device. This is, of course, challenging because your mobile device doesn't include a keyboard. So it's a cruder user interface, but you should be able to do anything that you can do on your desktop except for extensive programming and writing on your mobile device. It also means that we would like to address the needs of the next billion users. So who are these next billion users? First of all, they probably don't speak English. Second of all, they probably have paid very dearly for their mobile device, a lot more relative to their income than we do. And it also means that they may be accessing the internet only through their mobile device. And so the number of cell phones that have been sold in China and India, which are the top two lines, and if you can't read it, it's 250 million in the case of China, is one indication of that. But perhaps a better one is this graph, which shows that the Chinese are accessing the internet mainly through their mobile devices, and that crossed desktop access a couple of years ago. So mobile first is really going to become mobile only for most of the next billion people, and that's the challenge. So other things you could say is, first of all, they probably have relatively mediocre internet access, at least for the first few decades of this century. The cell phone gives us convenience. It gives them livelihood and power. So they're going to use these mobile devices differently than we do. And because my area is computational photography, I know well that the camera is an important part of this. So I could show a variety of info porn slides for that, but I think it's probably fairly obvious to you. So this one shows just how many images are uploaded to Facebook and Snapchat and Instagram. I'm afraid Google Plus is unfortunately a very small sliver there. 2 billion pictures being uploaded per day. But the way I prefer to think about it is this Kleiner-Perkins slide, which shows young people at a concert in the 1990s on the left and in the 2010s on the right. So they're no longer holding up their lighters or candles, they're holding up their mobile devices. So this is fairly obvious. The best camera is the one you have with you. You've all heard that before. Another important trend is that the mobile camera is becoming a tool and a weapon in politics. And so there's a course at Stanford called Liberation Technology. And we can all think of recent examples of the power of the cell phone, this from North Charleston and this from the Ukraine. And I don't need to say anything more about that. So wearable devices and wearable cameras are even more powerful than that. So let me take a step back for a moment. I gave this talk here about a year ago on Google Glass. I was wearing Google Glass, and I showed these slides that the camera was hands-free, that it was point of view, that it was always available, that it was instantly triggerable, and a few more subtle things like the fact that your eyes are unobstructed. So those two girls are looking directly into my eyes. They're not looking into a large piece of glass of a camera that I'm holding. And you can really see that in their eyes. So there's an emotional interaction. All right, well, those are the slides I showed a year ago. What happened? Why did glass fail? So you notice that I'm not wearing glass now. So I said last year that in order to be successful, glass needed to be lightweight enough, unobtrusive enough, fashionable enough, and useful enough to be worn all day long. And those were really hard requirements, although they just seemed like rhetorical buzzwords at the time. So in the end, it was lightweight enough, and I think it was fashionable enough, at least on someone like that. But the ratio of useful to unobtrusive was too low. In other words, for that goofy little thing hanging in front of your eye, it didn't do enough, or it didn't do it reliably enough to make a compelling product. And it was also too expensive to build. Interestingly, right, so smart watches need to be aware of this ratio of unobtrusive to useful. I think that battle is still ongoing. So interestingly, privacy, which has been in the news a lot, the whole idea around glass holes, did not turn out to be a factor in the canceling of the launch. It was really this ratio of unobtrusive to useful, and it was the cost of building it. All right, so that's all I want to say about glass. Let me get back to mobile. So there are a lot of challenges around mobile, and I think everything that's on this list you'll agree with. I'll go through some of them in detail, and so you can think of this as an outline for most of the rest of my talk. I've got a riff at the end on superhero vision, but I'll be mainly narrating this. But I won't go through all of it. In particular, the user interface parts of it I won't talk about today. I'll talk mainly about computing power and battery life, and I'll talk about connectivity, and I'll talk about the complexity of the computing platform. And so in some sense, you can think about this talk as being, why is computing research going to be so hard on a mobile platform, in particular with respect to the systems issues? So why is systems research going to be so hard in the next generation because of mobile platforms or on mobile platforms? And of course, a mobile might be tethered to a wearable, and probably will be once someone finally gets the formula of Google Glass correct, or a watch like this. And wearables have the same challenges, and they are even worse. And again, for today, I won't talk about the small display and the crude user interface. I'll talk about the systems issues. Okay, so let's get right to it. So performance, we have always worried about computing time in computer science, but power is actually the biggest limiter on a mobile device. And we can talk about power two ways. We can talk about power actually either as energy, which means cumulative usage, so it's in milliwatt hours, and the requirement that a mobile device has to last all day. And so here's a chart showing, it says milliamp hours, so watts are amps times voltage. So these tables that show milliamp hours for batteries, which is fairly common, just means there's some assumed voltage there. There's the Nexus 6 right there. That's what this table's about. So on the left side, it says in the thousands of milliamp hours. It's interesting to compare that then to watches. And the numbers here are in the hundreds. So the watches have about 1/10 of the battery capacity that the phones do, but they still have to last all day. And by the way, there's the Apple Watch. It's 205 milliamp hours. And so their ratio of useful to unobtrusive is going to be an interesting battle, and we'll see what happens there. It's going to be a big challenge for watches. Okay, So the other way to think about power is in milliamps or milliwatts. In other words, the instantaneous usage. And that's a limit for two reasons. One is because of the draw on the battery. You can't draw out more current per unit time than the battery is able to deliver. But the other reason is because when you draw out that power, it goes mainly into heat, and you have to dissipate that heat, or the device will fail. And that actually turns out to be the bigger challenge for mobile devices. And one way you can control that is by throttling back the clock rate of the CPU. And so if you, but the problem with that is that that's only one of the power draws. So I know you can't read the captions here, but if you just look at that one on the right, the screen is this little blue bar. And that's actually where most of the power goes. The CPU, the thing that can be throttled back, is this tiny little red segment right there. Nevertheless, it's a very concentrated source of heat, and so dissipating the heat from that very hot CPU is one of the main challenges of building a mobile device. And as an example of how this throttling happens, this is the same chip, an Apple A7, and it is shown on 3 different devices: the iPad mini, and an iPhone. Over time, what is the performance? And what you can see from all of these graphs is that as you run the same benchmark over time, the performance drops. And the performance drops because the device gets hot, and they reduce the clock rate in order to save the device from overheating, and so the performance drops. And this is true on all mobile and wearable devices. And so this is going to be a big challenge for phones. So you might think to yourself, well, all right, I know how to solve that. It's a mobile device. First, a couple of lessons. So heavy computing is okay if it's over quickly. Now, that's not something we usually think about in computer science. Heavy computing is okay if it's over quickly. But literally, quickly means before the device heats up. A second message is that mobile devices need a breakthrough in cooling, not in performance. So how do you get the heat away from the device? Or maybe you should split up the computing over multiple chips so that you can cool them independently. This is a real design challenge. All right, so one solution we might think of to this problem is, well, it's a mobile device. Why don't we upload the data to the cloud for computing? And then we can compute as much as we want to. But let's work that through for a second. So suppose you had a burst of images. I do burst mode photography as one of the technologies on my team at Google. And you've got 5 megapixel images, and you've got 10 of them. You could upload it to the cloud. So let's upload it as JPEG over 3G, which means cellular data. And it might take 50 seconds and consume 400 milliamps of power. And so that's over a cellular modem. Or we could compute on the device. And so for the same energy it took to upload those images to the cloud, I can compute on, let's say, this Android Nexus 6 for 100 seconds, because the CPU takes only 200 milliamps instead of the 400 milliamps of the radio. So half the power, twice the computing time, the same total power. So if you work that out, for 100 milliseconds at a 2.0 gigahertz processor times 4 cores, I could do 22,000 operations per pixel on every image in that burst for the same energy as uploading it to the cloud. And so the lesson here is it's almost never worth sending data to the cloud for processing. And that's a surprising result, but an important one as we design algorithms for the next generation of computing devices. Okay, so I'm going to start throughout this talk to leave a set of action items for computer scientists. And so the first one is embarrassingly parallel algorithms, such as the ones that I was taught in graphics here, are not a panacea on mobile. You actually have to find algorithms that do less work, or that do it quickly, so that you can get it over with before the device heats up. All right, let's talk about connectivity. So a cell phone might contain 7 radios. This one I think contains 6. So it's got the 2 cellular modems, Wi-Fi, Bluetooth. NFC means near field communication. That's the radio that does Apple Pay or Google Wallet. GPS is a location, and an FM means an FM radio. This one doesn't have one of those. More importantly, you want graceful degradation in functionality as the connectivity gets worse. And that's actually a hard challenge. There are several aspects of that. One is handing off between different radios. And this is technology that is still not very robust. You would think that the Google campus is well connected, but there are dead zones all around each of the buildings because the Wi-Fi gets weak as you walk out of the building, and it hasn't yet switched over to cellular data. Another aspect of it is progressive streaming. So the video codec community has gotten that pretty well, where they'll send you a low resolution or low bit depth version first and then send more stuff later. But display ads have kind of messed with that success, and so we're still fighting how we should do progressive streaming. This, of course, reminds me of progressive rendering in computer graphics. It's some of the same issues. So also the ability to use the device without the cloud is a challenge. And so an example of where that's a challenge is in voice recognition. So Siri is cloud-based. So is Google's or Android's voice recognition. It can recognize simple commands on the device, but most of it is sent up to the cloud. And that means that especially for a wearable, I can't command the wearable unless I'm connected to the cloud, or I can't say anything useful to it. And so that's a real challenge going forward. It's a big challenge in particular for wearables. So my second action item then is we need a moonshot. Sorry, that's Google X speak. We need a moonshot for better voice recognition or transcription on device. And the solution can't require a giant database. What I mean by the second line is originally voice transcription, like natural language processing, which is not my expertise, was based on a complicated set of rules. The revolution that's happened in the last few years is that it is now machine learning algorithm based with not many rules, but a very large database. That database requires a lot of storage, and so that's why Siri is in the cloud. What we need to now go back to is either a very clever way of coding that database or a hybrid of a database and a set of rules so that we can do it on device. And that problem has not been solved yet. So there's an action item. Another aspect of connectivity is ways of synchronizing content with the cloud. And there are a lot of different approaches one could take with that. Of course, some services like email or chat, you need to be connected. Another strategy you could take is to cache the most recent. So Google Docs uses that strategy. You could pin selected content, meaning I'd like this to be kept on my local device. And so Android Play Music and iPhotos works like that. But inevitably, the picture of Machu Picchu that I'd like to show someone on the airplane because I just got to talking to them about Peru, I didn't think of pinning to my device. And so I don't like that particular strategy myself. Or you could try to cache everything on device. So Dropbox and Evernote uses those strategies. That's a little bit hard for images and video, but it's certainly possible for text documents. So there are a number of computer science challenges that come along with these. If not all of your content is actually on your device, what do you do about indexing and searching? You'd still like to be able to search for it to find the document you want, even though you might need to download it. How about reliable synchronization, reliable security? So since your connectivity may come and go very unpredictably and repeatedly, it turns out to be really hard. And it's amazing just how hard synchronization is. And there are very few companies that have made completely robust file synchronization over mobile. Dropbox is one of them, at least in my experience. So let me leave as a third action item robust synchronization of large, diverse databases across multiple, intermittently connected. I know this is a mouthful, but each part of this is actually important. And if you leave out one of these factors, you're solving a toy problem. All of them make the problem harder. Okay, So mobile devices are insanely complicated. I know this sounds like a kind of an over-dramatic way of doing it, but it really gets at the heart of why it's going to be hard to do systems research in this area. So let me go into that in some depth. There are a lot of different kinds of computing resources on a mobile device. CPU, the graphics processing unit. DSP is a digital signal processor. VLIW, very long instruction word coprocessor, or a programmable image and signal processor that, despite its name, is actually increasingly hard to program as you go lower on this list. There are multiple vendors who barely talk to one another. So on this device here, my Nexus 6, there is face detection circuitry, probably based on Viola, that is intellectual property that's delivered to the system on a chip vendor, the second line, by some other company, and then put on the chip. So the system on a chip vendor is Qualcomm in the case of this device. And then that's integrated into a phone by Motorola in the case of this device. And they do further software as well. Then there's a firmware. Then there's an operating system, which is Android in this case. And then there are apps that are written on top of that. And so there are layers of abstraction, layers of hiding for proprietary reasons that make it an insanely complicated and opaque device. Unless you're Apple, in which case they all take place in one campus. So the software stack then is very deep, and it's deeper even than you think. Android has this unfortunate architecture that there are two languages, Java at the top and C++ at the bottom. And in order to do something very simple, and for me, I do cameras, so I wanted to lock the focusing lens on the rear-facing camera, and it was 13 nested function calls that go through this stack of vendors. I know because I traced them through. And the outer person doesn't even necessarily know how the inner function is implemented. Many functions are implemented in hardware, and that hardware is opaque and not necessarily reconfigurable. So let me give you an example of that. And the example I'll give is from the area that I know best, which is photographic technology. And let's talk about the enabling hardware technology for burst mode computational photography, which means taking a quick burst of pictures and combining them together in order to get higher dynamic range or better low light performance. So if you have an Android phone, the HDR plus mode is something written by my team, and it's an example of this burst mode photography. I'll show that a bit later. All right, so the enabling technology is the fact that you can read off the sensor at full resolution, which for glass was 5 megapixels, at full video rate, which is 30 frames per second. And you can process it at that speed to YUV, which is a three-dimensional color space, luminance, chrominance, chrominance. And then the viewfinder, which could be on glass or it could be on the front of this thing, is actually accomplished by processing at full resolution, at full video rate, and then downsizing for the screen at the very end of the pipeline. And so you might think, well, that's inefficient. You're throwing away all these pixels after you've computed them. The reason it's done that way is because there's hardware that can do that processing very fast, and it's not easily reconfigurable. And so let's take a look at that hardware and see how that's done. So how do you process full resolution at full rate to a three-dimensional color space in real time? So I'll give the example of Google Glass. So this is a Texas Instruments chip, but it's essentially the same diagram for a Qualcomm chip or an NVIDIA chip or an Intel system on a chip. So there's the system on a chip. Zoom into that. There's the architecture diagram. It's just a big bus. There are the ARM CPUs. There's the GPU system, and we're going to look just at the imaging subsystem. So there's stuff for video and stuff for still photography on that. There's a discrete cosine transform, for example, for video coding. And let's just look at the still photography pipeline. So there are hardware blocks in there for doing a variety of buffering and correction as it comes off of the sensor chip. So we'll just look at the latter part of this processing pipeline. I know this is getting very, very deep, but this is what is on the millions and millions of transistors that are on a system on a chip. So this might, if you are familiar with computer graphics, be reminiscent of the Opengl architecture diagram. And it is indeed as complicated. I'll show it, I think, as a list. It's probably a better way to look at it. So I'm not going to go through every one of these steps. Just I'll show, so one of them is demosaicing, because that's probably the term that's least familiar to you, where you take what's called a Bayer mosaic, a red or a green or a blue pixel at every photo site, and you interpolate the reds where they didn't occur, and the greens and the blues, so that you end up with a red, green, and blue at every pixel. And then there are a bunch of other steps there. And what comes out at the bottom is this luminance, chrominance, chrominance image for every pixel at full resolution at full video rate. All right, so here's the pipeline as it stands. If we could reconfigure it, what might we be able to do? So let me give you one example of why it might be nice to make it reconfigurable. So suppose, for example, I could tap out the Bayer raw image and then re-inject it later. Here's an example of how I could use that reconfigurability. I could, for example, use handshake to avoid demosaicing. So if you think about it, if I'm capturing a burst of images with my hand shakes a little bit. And so behind every viewing ray, over the course of, say, 10 or 20 frames, I will probably end up with a red, a green, and a blue pixel behind each direction of view, just from the natural motion of my hands. And so the algorithm might be read the frames, process them, raw is another word for Bayer mosaic, align the features with pixel precision, and hope that you end up with a red, a green, and a blue in every viewing direction behind every ray, and then re-inject it. And now you end up with higher resolution because you didn't have to interpolate the reds, greens, and blues at some of the pixels. Now, of course, then you need to reconfigure it a bit more to not do demosaicing anymore. So just a little bit of reconfigurability might lead to an interesting algorithm and a higher resolution final image, but it needs to be reconfigurable to do that. So the key is finding the right points of abstraction. So let me make an analogy to computer graphics. So in graphics, Jim Clark came out with his geometry engine, which did these 4x4 matrix transforms, and then an API, an application programming interface, was designed for that, which eventually became OpenGL. And then to provide fine-grained control, we came up with the GPU shading languages, the graphics processing unit shading languages. For a camera, one such architecture, which I'll describe in a moment, is the Franken camera. One such API is Android's Camera 2 API. What we don't have yet is shading languages, and so that's an interesting opportunity going forward. So let me describe that a bit more. Of course, the same thing you can imagine for computer vision, but we don't even have an architecture yet for computer vision. So there's an open challenge. So the Franken camera is an architecture that allowed you to send in a stream of requests to the sensor with, say, an exposure time and a sensitivity and a focusing of the lens for each request, and then you get back a stream of images and statistics about each image. So we came up with a little language, which is really just an API for that says to frames, different exposures, fire the flash in the middle of that one, and do that in a loop. So we took our already ugly Franken camera and made it even uglier by putting 2 flashes on the top. One strobes continuously, one fires at the end of the frame, threw up some playing cards, and my PhD student David Jacobs got this picture. So what's cool about this, aside from the fact that it's a cool picture, is that he did this in just a few hours, from hot melt glue gun to that picture, because he had an API that provided per frame control over the camera. Now, that's the Stanford Franken camera architecture. It is now the Android camera HAL. HAL means hardware abstraction language, which looks almost the same. It's got a series of requests that go into the architecture, and out come a sequence of image buffers and a sequence of metadata saying what exposure and focusing and so on was actually used. The API is unfortunately a little bit more complicated, but it does have calls in there for setting where the lens should be and what the exposure should be for every frame. What is the ID of this frame, and then you'll get back exactly the same sequence of frames. The way it used to be is you would set the exposure, and sometime later it would switch to that exposure, and you wouldn't know how many frames it got. So the synchronization is important. So this allows control over the camera. I haven't said anything about the image processing yet, and so we have only solved half of the problem with this architecture. And the other half is still an open problem, is how to accelerate image processing, what are the right points of abstraction for that. And in addition to the right abstraction, we need the right programming model. And so that might just be an API below which vendors can implement whatever acceleration they want, and above which we can do blocks like a Fourier transform, or a block like demosaicing or denoising. It might be a domain-specific language, a general language or a domain-specific language like Halide, which I'll describe in a moment, or it might be a lower-level language. So Halide is, just as an example, I'll use it. It happens to be from Stanford. It's a domain-specific language for image processing. And the idea of it is very simple. This is just a do loop to blur an image by a 3x3 window. And the two key lines are, of course, that one which is the horizontal blur, and this one is the vertical blur. Just keep those two lines in mind. It took 10 milliseconds to do that on a particular processor. We could speed it up by a factor of 10 by using intrinsics, which are vector parallel instructions. Here they are for an x86. That makes the code almost unreadable, as well as unportable. Or we could write it in Halide. They're the two lines exactly as they were before of the horizontal blur and the vertical blur. The loop indices are pulled apart into something called the schedule. And the schedule says, what are the loop indices? How would I like it to be vectorized and parallelized? And you might tune that schedule differently for different targets. A target would be a CPU or a GPU or something else. And so that also was 10 times as fast as the original code. Halide is spreading like wildfire. Now, if you ask Andrew Adams, who's on my team at Stanford, who was the inventor of Halide, he'll say, well, of course, it's because we can use Halide to write implementations of all of these well-known benchmarks that are 10 times faster than the benchmark. But a little bit more modestly, I think really the reason that Halide is spreading so fast is because it runs in the cloud and on device. It runs on iOS and Android, and it compiles to all of these different targets. And so all of these companies are starting to use it because it's one language that gives high performance for image processing that can be run on a variety of platforms. And so Halide might not be the final answer, but something that has some of these architectural characteristics are a good answer for this. We'll see what the final answer is, and I think that's an open problem. So let me summarize this with the action item. Neat architectures for accelerating image processing and computer vision, and good ways to program them. And I still think that this is an open problem. All right, so that goes through the outline that I gave you, but let me take my speaker's floor option here of just adding a few of my own kind of soapbox items on what I think are good challenges, mobile related, for the next 25 years. So in the last 25 years, I would argue, and hopefully you would agree with me, that among the largest successes in computer science are deep learning. And so deep learning plus big data is replacing hand-built algorithms. And I already gave an example of that, which was the voice recognition. And photography, I think, is a very interesting direction for this, and we'll see what actually happens. Another one is computer vision. Computer vision is finally beginning to work. And as a result, we're beginning to see things like Google image search that is not using the text anymore in your caption, but can actually find a cat because it looks like a cat. You can also find you can find algorithms that will allow a mobile device to recognize it, to compute its pose, meaning X, Y, Z, roll, pitch. I didn't get that right. Yaw, pitch, and roll. 6 degrees of freedom from the camera imagery in real time. And so there are a number of algorithms for doing this. Here's one from the literature where the camera's looking at that, and it's building up a depth map in real time. So Google's Tango project is an example of trying to do this pose estimation and build a 3D map at the same time, a problem called SLAM, simultaneous localization and mapping, in real time. I think in the future all JPEG files are going to include depth maps. So it's going to be RGBZ. And you'll be able to use that for a whole bunch of things. You'll be able to build 3D models in real time incrementally by moving around an object. And there are going to be lots of applications in virtual reality and augmented reality for real-time, low-level computer vision. One of my favorites that's already an app is WordLens. So this looks kind of like a crude app that does this real-time translation, but there's a whole lot of low-level computer vision going on there in order to be able to localize the text, align it, rectify it, isolate the letters, do OCR, optical character recognition on it, and then translate it. This is hard, and it's being done in real time. So it's kind of a mediocre translation, but the company was bought by Google, and so Google Translate is good translation. It does run on glass, it also runs on phones, and I think it's a good example of the success of low-level computer vision on mobile devices. So there's going to be pressure on hardware, there's going to be pressure on abstractions and programming languages in order to finish this revolution of low-level computer vision in real time, or high-level computer vision, although that's going to be even harder. There's also a brain drain on academia, particularly in the computer vision field. I know because I have recruited some of them to Google. Hopefully they'll go back to their academic institution when they're done so that we don't eat our seed corn. But this is happening, especially in the computer vision field, because of the successes in computer vision. And so I'll add another action item here, which is that the universities should allow faculty to either be part-time or to rotate through industry. This is the reason that I was forced to leave Stanford. And I can cite a number of other senior faculty at Stanford that have recently left. Stanford is less flexible than other universities. My colleague Steve Seitz at University of Washington, I'll give only a positive example, is 50% at Google and 50% at the University of Washington. And so he runs a big team at Google. He works with me closely. He runs a big team of graduate students at the University of Washington. They write great dissertations. They know what's important problems to solve. There are conflicts, but they're good conflicts of interest. They're not the bad kind of conflicts of interest. And academia in general needs to learn how to solve this problem well. And Stanford better take the lead on this, or they're going to suffer perhaps the most because of Silicon Valley. All right, one last soapbox point. Mobile systems are hard to teach. So I've been talking mainly about research, but let me talk about teaching for a moment. Why are they hard to teach? First of all, remember that stack of vendors that I talked about? So these systems are all proprietary. They're probably all the competitors are violating each other's patents, and so they keep everything secret so they don't know it. And in addition to that, they are originally electrical engineers, not computer scientists. So I don't want to dump on electrical engineers. I am jointly appointed in electrical engineering, but they think first about the elegance of their hardware and then about the software, whereas computer scientists would think first about the architecture of their software. And as a result of that, the software is not as well architected typically as if it had been thought about first. And that's a challenge going forward. And as a result of these two effects, there are few textbooks about mobile systems or mobile cameras, and few courses that are taught anywhere in this country. So when I try to teach a digital photography course about both the science and the art of photography at Stanford, I can't find a single textbook that describes how to do white balancing, which is shifting the colors in a camera so they look more natural, or exposure, or focus, or denoising. It's just not described. There are academic papers, and then there are what cameras really do, and they're not necessarily the same. And this is something that anyone from industry could show this same slide, that students are coming out of the university without the skills they need. Machine learning, I don't know if it's mandatory now at UNC. It darn well should be. It wasn't mandatory when I was at UNC, and I suffer for that every day. There are a number of other courses that should probably be mandatory at this point because of their importance in industry. At Stanford, the web development course is taught by industry visitors, and it's one of the most popular courses at Stanford. Security, natural language processing, and mobile systems. So Udacity's business model is kind of interesting in this respect. They bring in industry lecturers. that teach just what you need to know in industry. They have micro certificates in place of degrees that then makes it a very popular educational path for many students. And I think we're going to see a number of disruptive models here. I don't think it's going to kill the university, but it's going to be an interesting mix going forward. All right, so last action item then is develop platforms and write textbooks that enable the teaching of mobile systems, especially via lab courses. So my colleague Pat Hanrahan teaches a great course on computer systems using Raspberry Pi, which is an embedded programming environment. I see the thumbs up there on Raspberry Pi. This is hard. Look at the CS majors declarations at Stanford over the last few years. The same thing has happened with enrollments in our courses at Stanford. And so getting the small ratio of faculty to students that you need to teach this, especially in a lab course, is going to be extremely challenging. We must find a way to meet that challenge because that is what will keep computer science relevant. All right, so let me just finish with a very quick riff on superhero vision. So this is what camera systems might be able to do in the next generation if we can solve these other architectural problems and accelerate image processing and continue the revolution in computer vision. We could, for example, see in the dark. So this picture of Yosemite Valley was taken in the middle of the night. You can actually kind of see the stars there, and it was done with a very long exposure. Could you do this on a mobile device? Well, this was done on a tripod, but you could take a burst of pictures and combine them together. In order for that to happen, the dark current, the light that leaks onto the sensor, has to be very low if you do it in a single shot. If you do it in a burst, the read noise, the noise that enters the image as you read it off of the sensor, has to be low. But we're getting there. And so this is going to be possible in a few years. Here's an example. This is Georgia Tech professor Karen Liu in a room with the lights out and the door closed. And here it is by averaging a bunch of images together. And you can see the difference, I hope, in the noisiness of the image. It's because the noise goes down as the square root of the number of frames that you average together because of the statistics of photon shot noise. And so here's another example, the Lincoln second inaugural address. And here it is again, a single frame and a burst of frames. Here's the chapel at Princeton. Look especially at those two insets. And here it is if you average a burst of frames. So you can get much cleaner images, higher dynamic range by averaging it. This is putting a big load on the mobile system. We have to compute it fast because the device gets hot when I do it. Let's see, seeing through objects. So my favorite example of that is the cathedral in Helsinki. It's got these trolley wires in front of it. But if I take a picture like this, and like this, the trolley wires move around relative to the cathedral. I can align the images, kind of twiddle with their histograms to fix the color, and then just take a median. So median's like a voting filter. And if I have three images, the most popular color for each pixel in the sky is blue, not the black of the trolley wire. And so it can completely eliminate the trolley wires. Why don't all cameras do that now? Well, using the APIs that Google and Android and maybe hopefully eventually Canon and Nikon will come out with, they will be able to do this. Magnifying glass. This is harder because, of course, everyone would like to have a magnifying glass on their head, especially. There are lots of them if you Google for them. But how do you actually obtain this form of superhero vision? If you do it using a traditional zoom lens, it needs a long optical path. If you do it the way Nokia did it, where you have a very large sensor and you either downsize the image, which gives you a wide field of view, or take a small crop, which gives you a narrow angle of view, then you can do it, but you needed a very big sensor to start with. And so the Nokia phones are very thick. Super resolution, people keep playing with. It's an interesting area for research. I have not seen any results that don't look over sharpened. And the reason has to do with the diffraction limit of the lenses. Slowing down motion. So here's my dog. Slow-mo is so much fun. So The iPhone does slow-mo. Lots of other devices do slow-mo. It's a lot of frames per second. It's a lot of pixels per second. So it's an interesting mobile processing problem. But we're going to see a lot more of that. We're going to see higher speeds as well. Motion magnification. So this is work of Bill Freeman at MIT, where he took this input stream and produced this by computing the motion vectors, exaggerating the motion vectors, and then infilling the stuff behind it. So you can see the actual motions that were present at the left. This is hard. It took 10 hours to compute this video offline. Can you do this on a mobile device? And can you do it using a handheld camera? His group has published results since then of a slightly different form. This is color change rather than a motion change. This is your pulse that can be done in real time. And so, of course, the question there is how much signal-to-noise ratio is needed to detect this, and whether it's socially acceptable to run that on a wearable device. Face recognition, the last one I'll do. So if you met this guy at a party and he asked to borrow some money, would you lend it to him? And if you didn't know him, it might be handy to have this information pop up in your Google Glass version 2.0 or something like that. So it's still sci-fi to do this from an uncontrolled photograph. And I think the press misses that point. And Google proactively prohibited it, although, as I said, this wasn't a factor in the canceling of the consumer launch. It could eventually work. If it does, someone is going to build a device to do it, if not Google. And I think we just need to get over the idea of anonymity. But we don't need to get over the idea of privacy. And so the separation of information from one domain to another, the siloing of information, is going to turn out in the next generation to be more important than actual anonymity. And that's what will maintain our privacy. And it's going to be a constant dialogue between industry and society at large to solve that problem. And with that, I'll thank you for your attention. I'll be happy to answer any questions.
Why don't we just take one or two questions? Rich?
So for the mobile devices, you skipped over the user interface, but to me that's the part I can't even begin to wrap my head around. What are your thoughts on that?
Yeah, the question was mobile device user interfaces, what are going to be the hard challenges there? Obviously, the fact that it doesn't have a keyboard is important. The fact that you just don't see that much of your world, and so scrolling and panning around in it is going to be very hard. This is a pretty crude pointing device, and you could argue that this device was really never designed to do this. It was designed to hold something. It's as a tool holder. And so right from first principles, there are challenges there. And I think a good example is how long it took Apple to finally release cut and paste. It was several years after the iPhone first came out where Steve Jobs finally said, all right, this seems to work barely well enough, this method of cutting and pasting. I think that's just going to be a continuous ongoing challenge. And that's one of the reasons that voice is being investigated as a possible alternative. But it needs to be on device and it needs to be more robust. This is a wide open area for research. It's not any smaller than the challenges that I did show. It's just not something that I have as much expertise in, so I didn't focus on it.
So since we're running a bit late, we'll just take one more question. Steve?
Mark, how come handshake in replacing demosaicing doesn't quite blur itself?
It does. And so this phone has optical image stabilization, which moves the lens around during the single exposure and tries to correct partially for that handshake blur. But you can use a strategy if you do burst mode photography of taking shorter exposures. And the shorter exposure will have less blur per picture. Then you'll need to align together the features in the multiple pictures, and that's generally the strategy for a burst mode photography algorithm. And the shorter exposure works because the read noise is low. And so that shorter exposure is noisy, but not as noisy as it used to be. And so there are those ways of getting around that handshake blur. You could also try deconvolution, but that introduces more noise again.
Well, why don't we thank Marc again. He'll stick around if people want to ask more questions. The next sessions are down in the lower lobby of the Sitterson and Brooks building. I'll see you there.